first speaker in this session is Peter van der Kamp, and he will tell us about CAC and Backlund transformations.
Yes, I will. Thanks a lot for the invitation. I'm going to talk about 3 papers. That is maybe way too much. These papers you can download from this website here, and this word is the Dutch word for mathematics. So these are the 3 papers. They're joint work with Dajun, who I think is here. But the good thing about these papers is that they are very related to each other. So it's not too far stretched to give a talk on all 3 of them. CAC means consistency around the cube. So here is a cube. We will be dealing with lattice equations. So that means we have a lattice. Here is a lattice on the kind of ground floor. You can extend all these lines and you get a lattice. And then you have a lattice equation, which is a quad equation, so a relation between 4 points, u, and a shifted version of u. So we are thinking of u as dependent on 2 discrete variables. And if you shift one of the variables, you get, that's denoted by this tilde, and het is a shift in the other variable. So here are 4 points on the lattice. They satisfy a relation, which is a quad equation. And you can embed this thing in 3 dimensions on a cube. And if you do that, you have 6 equations on the 6 faces of the cube. And you have 3 different ways of calculating this value here from the initial values, which are the black dots. So u, v, u hat, and u tilde are initial values. You use the 6 equations to calculate v tilde hat in 3 different ways. And if you get the same value, the equation is called consistent. So the thing is, you can have different equations on the different faces. And there is a big difference between having the same equation on, say, parallel faces, and if you don't have them on parallel faces. So, but in principle, all equations can be different equations. So 6 equations, if they lead to the same value, you have a cube system, and that can be consistent as well. The Lexpair thing is really when equations on opposite sides or parallel sides are the same. Is there a question? Yes, Dajun is here. Okay, so this is the same picture, but we have another interpretation here. We can think of the system A and A on the back face as well, and B on the right face and B on the left face as well, as these 4 equations forming an outer Backlund transformation. If Q is on the bottom face and on the top face is the same equation, then that system A is B is 0 is an outer Backlund transformation for the equation Q. And you might be able to find a new solution, which is then the V solution from a given U solution using that Backlund transformation. If this Q is different than the Q here, so you have a Q star on top and a Q on the bottom, then you have a Backlund transformation, so a transformation from a solution to one equation to another equation. So if you take all equations kind of the same, up to kind of a trivial change of parameters and variables, then you can classify all these equations. This was done by Adler, Bobenko, and Suris, and they obtained a list. So this list is organized in 3 different types. You've got the H equations, you've got the A equations, and the Q equations. The Q and the A are non-degenerate equations, and the H are degenerate equations. I'll come back to that later. So I'm starting off, giving you an overview of what is known before I get into the new results. Here is a list that I took from Atkinson's paper on James's paper on Backlund transformations. And you can see some examples here. You have these are actually outer Backlund transformations. So this is the equation, the A equation. The B equation would be very similar, except you have heads instead of tildes. And together, those two equations will form a outer Backlund transformation for the equation Q30. So this is a bit of a list that where you can see you don't need to have the same equation on every face of the cube. Now, the next list in the same paper of James is a list of Backlund transformations. So this is non-outer Backlund transformations. So you have the equation on the bottom here is an equation in U. You have an equation on the top of the cube, an equation in V, and this is then the relation between them. And again, this is the A equation, the B equation you get by changing the tildes into heads. Then 2009, ABS Adler-Bebenke-Souris came up with a new classification where they did not assume the D4 symmetry or the tetrahedron property, but specifically put in this non-degeneracy condition. And they said that all equations in this class were already known. They are the equations of type Q. And you now allow more general transformations, and the type A equations that are listed are kind of inside this class of type Q. So they are related. Then Ball came along, a student of Bebenke and Souris, I think, and he looked at the degenerate cases, so the H equations. He looked at a priori different equations on each face of the cube, and he got a list of cube systems and a list of equations that are degenerate. So apart from the H equations, there is extensions of those with another parameter epsilon, and there is a D list as well of completely degenerate equations. Then I want to say that we also have more general or higher dimensional lattice equations. So these are not equations on a 2D lattice, but on a 3D lattice. And the same idea, you can ask whether such a equation is then consistent in a higher dimensional cube, so a 4D cube. And here are some examples. These are not the only ones, but they are nice ones. Lattice AKP and lattice BKP. So higher dimensional equations are there. There is also non-affine equations. So these are multiquadratic quad equations. We're in 2014 now, where Atkinson gave this list of multiquadratic equations. And here is one example where you can see that this equation is quadratic in every variable, and this can also be consistently posed on the cube. There are some sign choices that you have to make, but it is connected to kind of a unique evolution. Then we have multi-component quad equations. So now instead of using V's, we have X, Y, and Z's, and at every vertex of the cube, you have a number of components. So in the first equation, there are 3 components, and hence there are also 3 equations. So this is, there are 3 equations then on each face of the cube. And you put the same 3 equations on all the faces of the cube, and you still have this consistency, which is also nice. So the original idea has been generalized in many directions, I would say. And then we came up with the idea of multi-component extensions of CAC systems. Then we wrote a paper, and then a referee made this remark that actually a special case of this generalization was already in James's thesis. and he called it the trivial tuplets extension. So what he did was, you have a scalar equation, which is CAC, and then you take n copies, big N copies of this scalar equation, and you kind of mix up the values from different sides, and you kind of switch all these things around according to this formula. And that is actually just a little remark he made, and our paper you can think of it as maybe remarks at his remark, but we got some interesting results as well. And if you look at this formula and you add an arbitrary integer mod n a and an arbitrary integer mod n b here, you've got a more general class than this trivial tuplet extension, and that's what I'm going to talk to you about now. This is kind of the first paper that I wanted to talk about, which is multi-component extensions of CAC systems. So here is a CAC system. I'm usually against using numbering equations in talks. I think it's a bad idea, but I promise you there's only one number. So if you see the number 1, then just think of, okay, well, this is the picture where we have, you know, a cube with 6 equations on that cube. In this case, all the 6 equations are different. So Q star is different equation than Q. So very general. You can take a scalar equation of this form, and then you can think of, okay, well, let's instead of scalars, I take matrices, diagonal matrices as the variables. And so in this way, and then you can create a permutation matrix that just shifts all these variables around, and you can act with that on the matrices in this way. So you have this transformation TKU is just, you know, making a rotation of your variables, a permutation. So then you have the following lemma. If that system 1, that cube system is CAC, it's a scalar system, then in this slide, I have matrices, diagonal matrices, and I've applied all kinds of shifts on those matrices. And this system is then CAC as well. If you think of the cube, you know, the name of the variable doesn't really matter. So you can switch them around, and it is not difficult to see that this gives you a CAC system. Now, if you kind of insist that your the equations on the opposite faces are the same, then you have to be a little bit more careful. You have to restrict the permutations you can do. So this is a less general statement, but you can ensure that your equation has a Backlund transformation in this way, and that implies that you have a Lex pair for the system, and you can embed it in this lattice. So you really have a lattice equation where you can maybe find another solution using the Backlund transformation. So this lemma you can use to get multi-component extensions of the ball cube systems, where you have kind of 6 different equations on the cube, but you need the theorem to kind of generalize outer Backlund transformations for multi-component quad equations, or non-outer Backlund, just Backlund transformations between these equations. So what you get is something like this, the H1 equation. If you just take the first equation here, you think of U is equal to V is equal to W, you get H1. If you do this extension, you get this coupled system. There's a 3-1-1 extension. You can choose one. You can get 3-0-0 is not an extension. That's just the system taking 3 copies of the equation. But if you start mixing them around, you have a couple of options, and we can actually calculate the number of different systems that we can get in another slide. This I just wanted to show. You can directly write down a Lex pair. So if your equation has a 2 by 2 Lex pair, then your n component extension has a 2n by 2n Lex pair, and you can just immediately write down what that Lex pair is. So that is a nice thing. This I'm also going to go very quickly over, maybe not so interesting, but if your equation has D4 symmetry, then some of the extensions are equivalent if you kind of allow coordinate reflection. So these are coordinates. The coordinates are just the independent variables here. And then you get the same systems no matter which of these extensions you apply. You can count the number of extensions. P is the power set. This P is the number of primes in the integer n. So you take the power set, you sum over all the elements in that power set, and this is the product of the elements in that set, and that will give you the number of non-decoupled and decoupled n component extensions. You can get extensions of these 3D equations, and here are just some examples from AKP. If you do a two component extension, this is what you get, mixing up the variables here. And for BKP, this is what you get. And then this is probably the most interesting thing. If you extend your scalar equation to a multi-component equation, you can then go back. You can do a reduction, and there's different reduction that you can do. You can do a non-local reduction. So for certain equations with certain symmetries, you can do these reductions. And for H1, you get then 4 different non-local forms of the H1 equation. And these are just, again, scalar equations, 4 different scalar equations that you can get by first doing a multi-component extension and then doing a reduction again, in this case, a non-local reduction. Here is an example of how you can eliminate components. So this is could be a Burgers equation, a 3-point equation. If you then do a 2-component extension, you get, so if the blue is kind of the variable u, you can introduce a variable v, so you get 2 equations for 2 variables. You can then use the second equation, this guy, to eliminate the v variable. And if you substitute this equation in here and you also substitute it in here, you get a relation between the u variables of this point. So you go from an equation, a scalar equation, to an extension, multi-component extension, back to the scalar equation on a higher order stencil. And you can do this for ABS equations as well. So what we've done here is an example again for H1. If you take this 2, 0, 1 extension and you eliminate one of the variables, you get a multiquadratic scalar 6-point equation, which can be written as a quad equation in other variables. And this seems to be a new kind of multiquadratic equation that was not in the list given by James before. From the 2, 1, 1 ABS equations, you get scalar 5-point equations. So these are equations on a stencil like this across 1 point in the middle. It is quadratic in that point and linear, multilinear in the other points. it takes a particularly nice form for H1 or Q10. And these are actually all known equations. They're called discrete Toda type equations, but it is nice how you can obtain them from these multi-component extensions. Another thing, is Wolfgang still here? You get the 14-point king-sheaf equation from a 2-1-1-1 extension of AKP. Sorry, this should be BKP, of course. That is a copy-paste error. You get a 12-point equation from the two-component extension of AKP. Oops, I clicked on the wrong button. Sorry about that. And other things we did in that multi-component extension paper is to obtain multi-component cube Peng-Levé equations. And we talked about solutions for the multi-component extensions. And you can just get these solutions from solutions to the scalar equations. All right, I want to go to the next topic, which is how to get from auto-Backlund transformations to auto-Backlund transformations and torqued ABS equations. So what we are going to do is we're going to start with an auto-Backlund transformation for one equation, and then we're going to derive another auto-Backlund transformation for a different equation. So this will either give you new equations or it will give you new relations between known equations. We can start with the natural auto-BTs. So the fact that ABS equation is consistent around the cube means that the equation is an auto-Backlund transformation for itself. So if you start from there, what you get is torqued versions of these ABS equations. And in fact, what we found was that all these auto-BTs listed by James are in fact torqued versions of these ABS equations. So each of the equations in that list can be obtained in this way. Also, we have applied this method to degenerate auto-BTs, and we found some 3D consistent cubes which were not in the classification paper by Ball, so that seems to be not complete. And we found a multiquadratic equation instead of the multiquadratic ones that we have already seen. So one thing to say is that the Yatarinta distinguishes two types of Backlund transformation. A BT of solutions, if you can actually kind of discrete integrate from your solution to another solution. And the BT of equations is more what I'm thinking of here, namely the consistency picture. If your cube is consistent, then you talk about equations BT. So that's what we're talking about here. If you get your equation from the auto-BT in a unique way, then the auto-BT is called strong. If it gives rise to the equation but not uniquely, the auto-BT is called weak. And if it does not give rise to Q, then it's called trivial. There's another thing, that there are superposition principles. If you apply your auto-BT twice with different parameters, then your these new solutions also satisfy an equation. All right, so what is the trick? We start with a CAC cube with these four equations, A hat, B, and B tilde. So it means we have the same equation on opposite sides, and we forget about Q. So we have these equations Q, but we forget about them. So we start with just the A and the B equations, and we're trying to solve. So we can we can find the values of V hat and V tilde from A and B, setting A and B equal to 0. And then if we go further, we try to find U tilde hat and V tilde hat, then we get two solutions. And one solution is going to be the omitted Q equations. And you can write them in different forms depending on different variables. And one way of writing them is in tetrahedron form, but I will come back to that. The other equation is going to be some kind of weird equation, because it is not, we're not able to kind of get a decoupled system. So this other solution will depend on both the U and the V variables. And but they can be dependent on them in a specific way. So similar to the tetrahedron property, which I haven't explained, I realize, but will do soon. The R equations can be planar. So let me just get to the pictures and show you what it is. So for the R equations, they will depend on both V and U variables. If they depend on that in this particular way, where it depends on U hat, V tilde, and V tilde hat, then you can draw a plane through these points. So if there's no dependence on this variable, and in this picture there's no dependence on that variable, then we will call these equations planar. And similarly for the tetrahedron property, which means that your solution V tilde hat depends only on V U hat and U tilde and not on U. That's the tetrahedron property. You can see the tetrahedron geometric form here. Then that equation has that property. So these are kind of very similar properties. And the thing to realize is that you can take these systems of equations. A is B is T is A hat is B tilde is T bar to be equal to 0. Now this system is not a system on the faces of the cube, because T is a tetrahedron equation, but it's a system of 6 equations. It's defined on the cube, not on the faces, but it has the CAC property. And similarly for this, these other equations, these planar equations, the equations depend on both U and V, so they're not defined on the faces. But from these equations, you have 3 ways of calculating the last variable from the initial values, and consistency is consistency. So this is a kind of a new way of thinking about consistency, where you don't need to have the equations on the faces. But the beautiful thing of these equations is, and that is told in this lemma, but that looks too horrible, so let me get to the pictures. The thing what you can do is in these pictures is just do a switch. You can switch around the names of the variables, and if you do that in this way, so we're switching around these guys, we're switching around these guys, this is the picture you get. You then have an equation that is defined here, and it seems to be dependent on only U variables and not on the V variables. And the other picture in the other plane will then only depend on the V variables. So this is kind of process that we call torquing. And now you can get from these kind of weird R equations that were not defined on the faces, by torquing them, you get equations that are defined on the faces, because we're not changing the letters, we're just changing the variables in the equations. So that will give you a new equation, and you still have the consistency that is given by this lemma, and that's what happens. And the same thing happens from the from the tetrahedron property. So you get for any of the ABS equations, you get you have the tetrahedron property, and if you then do the switch, you get another ABS equation. So this will give you new Backlund transformations for ABS equations. And here is an example. So H1, of course, the simple example that we all love. This is the A and the B, the tetrahedron equation is this equation. And if you do the switch in this equation, so you say, okay, I'm going to write change V tilde into U tilde, and where is it? What else am I going to change? Oh yeah, the V hat is going to be U hat. What you get is actually Q1. So that means that H1 is forms a consistent cube with Q1 as well. The planar equation is this equation. So it is coupled, but after this kind of process of torquing, you get a decoupled version in U and another one in V. And that is a torqued version of the original equation here. So the place of U of tilde and hat is interchanged in this equation, and you have a shift of the parameters as well. So two ways of torquing, a symmetric one and an asymmetric one. The symmetric one will take the tetrahedron property and will put that into a new equation. So for H1, that is Q1. And the asymmetric torque will take H1 and will take it into a torqued version of H1. So these are then the cubes that you get. You also get a superposition principle. So the original equation H1 is a superposition principle for all of these torqued versions. And there are two here. We see Q1 appearing. And these are the complete results. So this can be done for every ABS equation. If you start with H1, well, you get a torqued version of H1. And there is this additive. This A stands for the additive transformation of the parameters. And in each case, the tetrahedron property gives rise to a Q equation. Now, for some ABS equations, this list is not complete. Q3 is missing, A2 is missing, and H3 is missing. You need a different parameter transformation. It's a multiplicative parameter transformation. So we see PQ here. But in those cases, we also get torqued versions of the equations, and we get the tetrahedron property also gives you a new cube. So some of these cases will explain the transformations that I listed before, given by James, but there are a few more that were not listed by him. Yes, so this, I applied the technique of torquing to the natural auto-BTs. You can apply it to non-natural auto-BTs. These are degenerate. This is the table there. And you can apply it actually to this multiquadratic equation, H3 star. In our case, we have this torqued version of that equation. And we can do two different torques, a symmetric one and an asymmetric one. In the symmetric case, we get a multi-quartic system. You have the sigmas here. You have to expand this equation. It becomes huge if you want to write it without these parameters, but it is a quartic equation, and there is an asymmetric system as well. Now, this is the last paper I wanted to quickly talk about, where we explicitly use this, or the second cube for H2. You can get a kind of flipped version of this. So you can think of H2A, this torqued version, instead of thinking of it as the Backlund transformation for Q1, you can think of Q1 and the torqued version as a Backlund transformation for H2A. So the torqued equation is not only a Backlund transformation, but it's an integrable equation itself. And you can use this cube and, you know, rotate it a little bit, and you have to be careful. But every Backlund transformation is an integrable equation itself, and every Backlund transformation has a Backlund transformation itself. And you can use that to generate solutions. You can use it to calculate a Lex pair. So this is the Lex pair for this torqued version of H2. And here are some one-soliton solutions for the torqued version of H2A. So this is an equation that is not in the ABS list itself. It doesn't have the D4 symmetry. You can use these new kind of Backlund transformation to find solutions as well. So this is all I wanted to say.
Thank you, Peter. Any questions for Peter?
May I ask a question? I was wondering about the torqued versions, which is a very nice idea, by the way. Thank you for talking about it. You mentioned several times that they don't appear in various lists. I'm wondering, in the ABS classification, what was the condition that could have led to this? Were there too many restrictions in the classification work that Adler, Babenko, and Suris did?
So the first classification, of course, required these D4 symmetry. These equations don't have that symmetry. The equations appear in the balls list, the extended things.
Right.
But so the equations are there, but the cubes that I'm talking about are not necessarily there. So all these cubes are there. They are special cases because you have this parameter epsilon, and in this work, all the equations have a Backlund transformation. We wanted the opposite sides to carry the same equation because then you can embed it and actually use it to find solutions. But Ball goes a bit further. He does not require these equations to be the same on the sides. So he's got this extra parameter, and for non-zero values of the parameter, you don't have that. You can still embed it, but you have to take copies of the cube and flip them and put them side to side, and in that way you can embed it. But as such, the cube system itself, you have to do something to embed it. Let me see. I haven't answered your question. I feel somehow we haven't been able to find these equations in there. So it would seem you can set one of the parameters to 0.
I see.
But the equations are definitely in there, but the cube systems, we haven't been able to find it in this Ball classification.
Mm-hmm.
But so the torqued versions are not new, but the cube systems are. That's the thing.
Mm. By cube systems, you mean multiply.
So 6 equations on a cube that is consistent around that cube.
I see. Okay.
Yeah.
Thank you.
Thanks a lot, Peter. It's really amazing to see how many ways this classification can be generalized. I want to ask in particular about the thing you said, that the equation could be on the cube, but going beyond just the 4 vertices of a face. So are you saying that there is a condition that links, different lots of the different subsets of the 8 vertices other than the 4 that are on a face?
if you look at, for example, these Bertini systems, these are all defined on a quad, but there are more components. Now you can eliminate these components, and then this system, for example, would be a scalar equivalent to a scalar equation on a 9-point stencil.
Yeah, well, that's actually where I was heading, because you've also done a deal of work on different stencils. So
Yes.
I was sort of wondering if in some senses, if I think of building a cube from just the usual thing where you fold up squares, is it sort of like your other stencils are somehow a different folding around a cube of, can they be obtained from a relationship on a cube that doesn't just operate on a quad? Maybe I misunderstood what you're saying. So in other words, is your equation on the cube, are you now saying that you have consistency around a cube, which is still about finding multiple ways to figure out what is happening on a particular vertex, but now the equations are not defined on a face? They look beyond a face. They look at vertices on two faces or something.
Yeah, so that picture here, we have instead of equations on the faces, we have 4 equations here. There's one equation which is just the A equation, one equation here, another one, here's another one, and here's another one. But now there are 2 equations, not on the bottom or on the top face, but there's an equation on this diagonal and an equation on that diagonal.
Right. Okay.
And it doesn't make sense for a quad equation. It only starts to make sense after you have torqued as a BT and as an integrable equation. But before you do the torque, it just makes sense as a consistent system. Okay. So you have the consistency. You can start with your initial values. You can use these equations to get 3 ways of calculating the last vertex. Mm-hmm. It makes sense in the consistency thing. It doesn't make sense as an equation that you would like to study on a lattice. Mm-hmm. Or on any other structure. I don't think there's a lattice that you can, it just breaks down. You can't extend this to a whole lattice. Mm-hmm. Only after you've done the torquing, you get what you want. You get again an equation on a lattice.
Okay. Yep. All right. Thank you.
Yeah.
Peter.
Yes.
Would you mind I give a comment?
Yes. Go ahead.
Okay. It's
you can point out all my mistakes.
No mistake. Just some extra comment is Adler is the ABS Adler. Before the ABS paper, he had a classification for the total type equations, and he got some list. And we have 2-component ABS equations, and by eliminating one component, and we can get 5-point equations or 6-point equations.
Yeah.
I remember that is all of those 5-point equations are nothing but the Adler's classification for total type equation, exactly the same.
Yeah, absolutely. Yeah.
Yeah. I think we mentioned that in our paper. Yeah. This just my comment.
Yeah, no, that's right, and I think I mentioned that these are not, but the other ones, the 6-point equations, they are more interesting. I think these are new equations. These are multiquadratic equations that are not the ones that James came up with, and others.
Yeah.
What is in your background, Peter?
It's called the Bertini incidence. So it's a curve of degree 4, the white lines, And then there's a pencil of infinitely many curves of degree 3, which have the same base points. And there are two special points that is that's a unique intersection between the curve 4, degree 4 curve and the degree 3 curve. That is a unique one. And if you take the line between that intersection, unique intersection, and the triple point on the curve of degree 4, then that line is tangent to that curve. So that is the Bertini incidence.
Yeah, that's a great background, Peter.
Thank you for the question.
Thank you, Peter. So let's thank Peter.